Hey guys, Mr. Betts here. I'd like to introduce you to something called parametric equations. Parametric equations are another way that we can represent relationships in the XY coordinate plane. So we're used to what's called a rectangular relationship that essentially has an equation that has x's and y's in it. And most of the time we're dealing with functions, which is going to be y equals something in terms of x. So y equals x squared plus 1 gives us a graph of a parabola, for example. In parametric equations, what we're going to do is we're going to have two different equations that represent an x coordinate and a y coordinate in terms of a third variable that's called a parameter. So that's why we call it parametric equations. So the parameter in this example here is t. T is a pretty common parameter to use, but it doesn't have to be t. Usually t represents time. These parametric equations are really good for representing motion of objects in the xy coordinate plane with respect to time. And it gives us an extra dimension and allows us to not only see where an object is, but when it is at that location. So the idea here is we have two equations, one that defines x in terms of t and one that defines y in terms of t. And into those equations, we can plug a value for t in. So I'm going to choose a simple one here to start with. Let's say we plug 0 in for t. So if we plug 0 in for t in each of them, we get 0. I know I have approximately equal to 0 here, but it's actually exactly equal to 0 for this. That approximation is going to be used later on when we're rounding. And so with plugging 0 in for t into the x equation and into the y equation, that gives us an x-y pair that can be written as an ordered pair, and that ordered pair represents a point. So at t equals 0, we have on our graph the point 0, 0. And what we can do then is we can do this with various values of t. So if I change t, you're going to see here that t could be pretty much anything, but I'm going to change it to, let's say, t equals 2. And as I slide it along here, you can see that we're getting different x and y values. So when t equals 2, x is going to be 3, y is going to be 4/3, and so we get a point in the xy coordinate plane at 3, 4/3. So notice that we're still graphing in the xy coordinate plane. We're just graphing an x and a y coordinate that depend on a third variable t that's not actually represented in the coordinate plane in the graph. Now, if I take all of these points here that I get as I just choose different values for t and plug it into the two equations, then we get a graph. So if I put all these together here, this particular example, we're going to get a graph that looks like this. So the idea, again, is we have equations for x and y, and both of those are defined in terms of a third variable, a parameter, in this case t. And for any particular t value, we can figure out what x is, figure out what y is, get an ordered pair, plot it in the coordinate plane, and then we put all those together and we get a graph. And you can see here that this particular graph does not represent a function in the traditional sense. So even though the x equation and the y equation, each of those by themselves are functions of t, the graph that we get multiple y values for different x values, and that means that it's not a function. However, we do get a graph, and we're going to want to do calculus on graphs like this. So we're going to be able to take a graph like this and pick a point and say, what happens if we want to look at the tangent line to the curve at that point? So that wasn't great. Let me try that again here. Oh, no. So if we pick a point here, I want to know what's the slope of the tangent line. The tangent line, when we're dealing with parametric equations, is still going to be represented with a derivative dy dx. So that's going to give us the slope of a tangent line. But you can see we might have a little trouble with that because we can't find dy dx with either of these equations when they're not related to each other directly. And that's going to be the challenge that we have in section 9.1.